Hello, everyone. Welcome back. Okay, what are we going to talk about today? So we are going to finish up the recommendation system topic. Then we are going to go into social networks. Okay. All right. So recommendation systems. Right. This is the one. You should be able to find the slides on Piazza. So recommendation systems, we have talked about content-based systems, which is very cool, right? You would be now, I'm pretty sure, well, most of you would be able to take large numbers of documents, generate features without any human tagging or human annotations. You can use all these features to build a recommendation system to recommend news articles, blog posts, any text document, right? And the features that you can use is TF-IDF words. For other types of content-based system, you will then need to rely on your metadata. Could be size, well, could be price of an item or other types of descriptions of an item. Then we talk about collaborative filtering. In collaborative filtering, we have this user-based method, item-based method, a model-based method, right? So model-based method, we didn't really go into the techniques, but you will be able to try this one from Spark. And for user-based and item-based, those are pretty straightforward. The only thing that you might want to take a deeper look at is how you will be able to use Pearson correlation to generate the similarities between items and users. And we said that sometimes you don't just stick to Pearson correlation. You can try cosine similarity and other similarity measurement. Maybe they work better for your data set and application. Okay, so collaborative filtering is the most popular method for building a recommendation system. And it doesn't require you to have any way to describe the content. So we talk about the pros and cons for content-based systems, the pros and cons for the collaborative filtering systems. And today we're going to go through hybrid approaches. So hybrid recommendation systems, in general, in a hybrid recommendation system, the system would include two or more different types of recommendation systems and a way to combine the predictions. It could be a linear model. We are going to talk about this later. So some example here, this is adding content-based method to collaborative filtering. So think about why we need this type of hybrid. So content-based method is really good at describing new items, right? Because content-based method are able to describe the content of an item even before anyone has rated that item. For collaborative filtering, it cannot deal with new item problem, but it would be able to recommend to generate a better recommendation quality. So some approach would just first use content-based method and then combine with some collaborative filtering, see if the combination will be able to better handle certain data types or data sets for an application. So we are going to look at some of these examples today. So this is the reading that you have to read. It will be in your quizzes and in your exam. I don't want it to be, but that's the only way that you will read it. This is a very interesting and important paper, because in the paper, although it's an old paper, but in the paper you can see they talk about different types of hybrid recommendation systems and real applications. So this is very good that next time when you see a similar problem that you want to deal with, you can look at the paper and see how people built their recommendation systems. It might be useful for your problem as well, and also for your final project. So there are, if I remember correctly, there are 7 types of recommendation systems defined in that paper, and we're going to talk about each of them today. And just a side note, this is not the gold standard of a hybrid system. These categories of hybrid systems is there to help you understand what type of hybrid that you can build. So if you can invent something else, that is great as well. So the first one is called weighted hybrid. This one is very simple. In a weighted hybrid, you're going to have multiple recommendation system or a recommendation component. And each of the component will generate a score for a given item. Then in the overall system will combine the multiple scores using some linear functions. And this means we can combine evidence from both recommendation systems in a static manner. That means the weight doesn't really change. This is appropriate when the component recommendation systems has some consistent relative accuracy across the product space. So this is the important part. So this is our first hybrid system, but I want you to be able to think about this way. Okay. So if you look at different types of hybrid recommendation system that will be introduced today and also in the paper, it will have some assumptions, right? So assumption is here. This tells you when you should be able to use this type of recommendation system. And here is the real method, right? So this is how to use it. So let's look at some example. A movie recommendation system in one of the reference in the paper has 2 components. The first one is collaborative filtering. Let's look at the second one. Second one use some simple semantic knowledge about the features. So this is more content-based, right? You have some semantic knowledge about your item's feature. All right, so what do we do with the collaborative filtering? Collaborative filtering technique identifies similarities between rating profiles. So users' rating profiles make predictions based on this information. Okay, great. So collaborative filtering. The second one use some content information with some latest semantic analysis, so compressed content information, and then recommend movies that are semantically similar to those that the user likes. So this is purely content-based. And the output of the 2 components is combined using a linear function. So in this example, what does it mean that if 2 components would have consistent relative accuracy across the product space? Well, because your final result will be, say, your first collaborative filtering give you 5, the second one content give you 2. And since you already have some data that you are testing, you know that, okay, you want to trust your collaborative filtering more than you trust your content-based system. And you say, I want to trust this 80%, I want to trust this content-based 20%. So eventually you just do a weighted sum, right? 5 times 0.8 plus 2 times 0.2, and you have your result. So, but this means across all the user and item space, these 2 weight, they do not change. So if we look at here, well, in the paper and also in the slides, often there is called in training phases, but sometimes you don't really need to train it because this is not the same as training in the machine learning, in the sense of machine learning. Okay, so not all algorithms include the training phase. So look at this. You have some data that you already know users' preference. You take the weighted hybrid approach. I'd say this is a CF recommendation system. This is a content-based recommendation system. This generate 5, this generate 2. And in your training data, you know that the real answer is 3. So what you want to learn is the weight here and the weight here, right? So once your system are able to see more data set, it will be able to learn 2 numbers here that will be able to generate the best static combination of the weights from 2 systems. Oh, okay, and one more thing. So sometimes we talk about candidate generation in a hybrid system, and in some hybrid system, this looks really complicated. So I'm going to ignore some of the candidates when I talk about them, but just bear with me here. If you have any questions, just let me know. All right, next question. So the question is one user based and one item based here, so they can be combined? Well, this weighted hybrid, usually you will use 2 very different recommendation system. User-based and item-based are still both collaborative filtering, right? So they share similar pros and cons. So if you want to combine 2 recommendation system, usually you have, for example, CF and content-based. Then you will be able to see, they will be able to complement each other. All right, so here, weighted hybrid. Okay, let's look at the chart first. So you have some user profile, and from the user profile recommendation system, for 1 will generate some candidate. Recommendation system 2 will be able to generate some candidate. Then the system, the overall system will take this 2 candidate list, merge them using either union or intersection, generate a final candidate list, and then generate a weighted score. Okay, so for example, let's say this is CF-based method. This is content-based method. So for this user, CF-based method says, all right, I am going to generate some candidate, and the candidate would have predicted rating, will have a predicted rating larger than 4.0, because we only care about the high rating ones. So this first list 1 will have, let's say, 10 movies. And the second is content-based, and content-based also will use the same threshold, so 4.0. The second recommendation system generate a list of, say, 8 candidates, 8 movies. So then you have a choice, right? You want to be able to combine the result and show it to the user with your predicted rating. So how are you going to combine these 2 lists? Well, 2 approaches. You can do a union, you can do an intersection. Think about this. What would be the problem of union, and what would be the problem of intersection? Well, if you have the slides, you should already know, but let's look at the slides. So intersection, if you take the 10 movies and 8 movies, and you are making an intersection to find movies that appear in both lists, this will probably be only a small number of candidates, right? It could be only 1 or 2 movies. Why is that? Well, the reason is in a weighted hybrid or in the hybrid system, you are usually combining 2 very different recommendation systems, so that this 2 candidate list should be different, right? So the intersection will be small. If you use union, what would happen? Well, if you use union, some cases would be possible for 1 recommendation to rate on a given candidate. For example, for your content-based system, because you do not need any previous user rating for a movie, say it's a new movie, you are able to recommend it, right? And if you ask your CF-based system to say, hey, what would be your prediction for this new movie? Because I want to generate it, I want to generate a weighted average. Your CF is not able to generate a prediction because it does not have any previous ratings for that movie. So in this case, you will need to give the candidate a neutral score so that you will be able to combine the scores from both recommendation systems. So during the scoring time, each candidate is then rated by the two recommendation system like this. So you take the candidate, either you do a union or intersection, you send them to a recommendation system again, generate a score, have the weighted combination, generate the combined score, and you are done. So if you look at this slide, this one, the recommendation system is taking the candidate and generate a score, right? But if you look at here, you actually already have the score. You take the user profile, you look at the recommendation system. When you are using the recommendation system to generate a candidate, you already have the score. And this is not a problem in the diagram. The diagram here is to show you that, okay, this is your workflow to build a hybrid recommendation system. But of course, if you want, you can combine multiple steps together so that you do not have to generate candidate first and send the candidate back to the recommendation system again and generate a score, right? Because in practice, if you're really building this, you don't have to process them again. Each candidate come with a score from the original recommendation system when you were generating the candidate. So this part might be confusing but you want to try the diagram, think about the data flow, and you should be able to understand. Or you can watch the video again. All right, so weighted combination. In the paper, the classification discuss only static linear combination of weights, but more generally, your weights doesn't have to be linear, right? It can be a neural network generate some scores, or it can be weighted majority voting, weighted average voting, so any way that you can combine the score. Or sometimes people can use dynamic weighting. Like the weight would change over time once you see more examples, more you have more training data and see how users respond to your recommendations. But the problem of that is you would need to take more time to process and update your system. So some Ptango system, initially they have a content-based system and a CF-based system. They have equal weight. So that means they trust both systems with the same amount of confidence. Then you can gradually adjust the weighting as you start to have more predictions and when the users start to give you feedback on your predictions. And maybe here you can use different weighting scheme for every user, right? So some user content-based system might works better for some users. Other users, you might use collaborative filter. Okay, so weighted hybrid. This one is very useful and very simple to implement. You can consider use this one for your final project. The second one is called mixed hybrid. In the mixed hybrid, these are recommendations of different component, but they just put the recommendations side by side in a combined list. So there's no attempt to combine evidence between recommendation systems or different recommendation component, and there is no weighted score. So one example here is recommending TV shows, or this PTV approach has content-based and collaborative filtering methods, but because of the sparsity of the ratings and the content space, it's sometimes difficult to get both recommendations systems to produce a good prediction. So instead of using either one or generate a weighted sum, this approach will just present both candidates to the user. So look at this chart again. You have some user profile, the recommendation system, say this is CF, this is content-based, they generate candidates, the same candidates, send back to the recommendation system again, and generate two lists, combine the list, and show it to the user. If you look at this chart, this is exactly what I said about having all these duplicates. So you don't really need to do this. Right? In practice, you just take the user profile, send it to recommendation system, and it will generate a ranked list. Send it to the second recommendation system. It has a ranked list. You combine them, you show that to the user, and you're done. And again, the reason why you see all these duplicates, the candidates and the scoring part, candidate generation part, is because in the paper, they want to be consistent across all the different types of hybrid systems. So don't get confused. All right, switching hybrid. So in a switching hybrid, the system will select a single recommendation system from a large set of recommendation systems based on the situation for the recommendation. So for example, for different user profile or item profile, they might choose a different recommendation system. This takes into account that the individual recommendation systems may not have consistent performance for all type of users or items. For example, we know that content-based systems works on all kinds of items, right? And we know that CF-based one works on items or users when you have many ratings. So if you have items or users that has many ratings, this will be the criteria you can use. You can say, all right, for this case, I will go with CF-based system. If they don't have many ratings, maybe new items, new users, I'll just go through the content-based systems, okay? So the assumption is you have some reliable criteria for that decision, for this switch decision. So in my example here, my decision is based on the number of ratings you have for users and for items. So this could be confidence values from the recommendation system, or depends on your recommendation system. Sometimes you have a confidence value. Or think about, in your Pearson correlation, right? Very many times you need to look at correlated items or correlated users. If that pool is very small, you say, all right, I don't trust this. This is not reliable. Then you switch to content-based one. So one example here, Newsdude recommend news articles. It has 3 recommendation component: content-based, and use nearest neighbor, collaborative recommendation, and a second content-based algorithm, use a naive-based classifier, right? Remember, we talk about decision tree. Although these two are they are content-based, but after you generate the content features, you have many ways that you can compare them to find the item profiles that are the most similar to the user profile, right? Nearest neighbor is very similar to what you can do using cosine similarity or Pearson correlation to compare user profile to all the item profile, and you find the one item profile that's the closest to your user profile, okay? Nearest neighbor. Naive-based classifier is a machine learning classifier. So you take all your user profile, look at all the items that the user liked before, and train a classifier to predict for the ratings. So it's more on the machine learning side. And the recommendation systems are ordered. So nearest neighbor technique is used first. If it cannot produce a recommendation with a high confidence, then it will go to collaborative filtering, and then naive-based approach. So if you look at this, okay, awesome. They tell you a way to prioritize it, but does it work for your own application? Maybe not. So if you're interested, look at the paper and see why they make this decision. You want to see their assumption about their data set and their assumption about their application so that they they came up with the decision of order their recommendation systems this way. So the diagram looks like this. Again, there's many duplicates here. You're going to send the candidate again to the recommendation system. So you have some user profile. The user profile sent to the recommendation system, it generates some confidence score. And you have some selection criteria. You say, all right, based on the confidence score, I will select one of the recommendation system. Let's say the selected one is here. User profile, again, going to the recommendation system, generate candidate, going back to the recommendation system and generate a score. Okay, cool. But it's actually just look like this. Right, so you have a final score. This is your output. This is your input. You have multiple recommendation system. You send it to recommendation system. It generates score and confidence at the same time, right? Your recommendation system will not just generate confidence. It always generates scores and confidence if it generates confidence. Then you have some selection criteria and you pick the one that's the highest confidence, then you just use the score, okay? So again, this chart with many duplicate components here is just to help you organize different hybrid systems. So don't get confused. Yeah, I think this is the third time I talk about this. So if someone's still asking this question, I'll be very disappointed about my ability to explain this. So please think twice before you ask me, why are we sending the recommendation system result back to the recommendation system again? All right, feature combination number 4. Here we want to send, we want to generate some recommendations, for example, from collaborative filtering into an algorithm designed to process data with a different way, such as content-based. So for example, your content-based system usually work on some explicitly defined content features, right? TF-IDF words, colors, price, but you can actually use your recommendation USCF system to generate some features and use that as the content to describe items, then use a content-based system to make the final recommendation. So that's why we call this a virtual contributing recommendation system or recommender. That's this one. So features would ordinarily be processed by one recommender are instead use a part of the input to the actual recommender, right? Let's say this is the content-based one, this is the CF one, generate some result and use it in the content-based system. So the idea of hybrid here is the hybrid of knowledge sources. Borrows the recommendation logic from another technique rather than use separate components to implement it, right? Remember before the different types of hybrid, if we want to combine CF and content-based, we just run it twice. But now we do it once. We take some training data, we say, hey, here is a contributing recommendation system. It will help us generate some feature, and this feature will feed into the actual recommendation system and make the prediction. The example is much clearer than the definition. So let's look at the example. So here, the recommendation system Ripper learn content-based rules about the user likes and dislike. The user likes and dislike works like this. So this is some collaborative features, right? So like user 1 and user 2 likes movie X, and this can become a feature for your movie X. And if you look at the definition here, this is actually just collaborative filtering. But if you treat this as a feature of movie X, you'll be able to use content-based system to process these features and make a recommendation. Right, so for example, like actor 1 and actor 2 start in movie X, right? This is your original content-based feature. You have actor 1, actor 2, and just put 1 here for your movie X, right? But you can also use some rules like this. You say, okay, user 1 likes it, user 2 likes it, and so on. right? This is not from the original content of the item, but it can be a part of your item profile or user profile. So then your content-based system, recommendation system, works in the typical way, build a learned model for each user. And here user rating data is combined with the product feature like this. And this, right, this is the product feature. So the content-based recommendation draws from a knowledge source associated with collaborative filtering techniques. So sometimes this can be very useful. So this is feature combination, combining different types of knowledge sources. Feature augmentation. Feature augmentation generate a new feature for each item because we are augmenting the feature by using some recommendation logic of a contributing domain. So again, you have a contributing recommendation system. For example, what you can do is you can use the association rule mining over the collaborative data to derive new content features for content-based recommendation, right? Like we did before. At each step, your contributing recommendation system will intercept the data and augment it and send it to the final recommendation system. And here there's no raw, there are not raw features as in the feature combination, but it's the result of some computation. I will show you what does this mean. For example, here the content boosted collaborative filtering will first learn a content-based model over the training data. So this is the contributing recommendation system. And then once you have the content-based model, you'll be able to make predictions, right? Once you are able to make the predictions, you can start to predict for unrated items. And when you start to make prediction on the unrated items, and when you keep the high confident one, although you might not be able to make good prediction for every item user pair, but for many of them you can have a high confidence prediction. And in that case, you will be able to produce a dense utility matrix, so making a set of profiles that are very denser than before, and hence they are more useful for collaborative filtering, right? So augmentation. So think about this. This is your original utility matrix, and this is a really sparse and large matrix, 1 million by 10 million, for example, 10 million users, 1 million items. And the first content-based system will help you to input or predict some of these values so that you will not have that many missing data. Then this way, your original matrix is augmented with all these predictions. Then you can use a collaborative filtering method on the augmented data. So you can use them when you have a well-developed, strong primary recommendation system component. In this case, will be the CF, and you want to add desired knowledge, add the additional knowledge source, so that the input to this recommendation system would be better than just using the original raw data. And these augmentations can usually be done offline, so you will not sacrifice any online performance. Some content boost CF example, you can use naive Bayes as the content classifier, fill all the missing values in the rating matrix, then form a pseudo rating matrix. This is the augmented pseudo rating matrix. The observed rating, they do not change, but the missing data are replaced by the predictions of your content-based predictor, this one. Then you can make predictions over the pseudo rating matrix, use weighted Pearson correlation based CF. You can give high weights for the items that are more user rated, or give high weights for active user, or for the original ratings. Okay, so augmentation. I want you to think about the differences between augmentation and combination. Although they looks the same, but read the paper and get into the real applications of these two categories, and you will be able to understand them. All right. The next one is Cascade Hybrid. This one is simple. So this one is a hierarchical hybrid. You have a weak recommendation system. This weak recommendation system cannot overturn decisions made by the strong recommendation system, but it can refine them. For example, you can break ties, and it has an order dependency. You run the primary one or the strong one first, and you run then you run the second one, the weak one, to break the ties if you need. So a cascade recommendation system uses secondary recommendation system only to break ties in the scoring of the primary one. For example, in this restaurant recommendation system, it's often return many equal scored items, and they could not be ranked relative to each other. So you don't want to return many options to the users, right? Rather than adding additional labor-intensive knowledge engineering to produce more features or produce more ratings, the hybrid system will just add a collaborative re-ranking of only those items with equal score, right? So you take all these items with equal score, you ask a collaborative weaker recommendation system to rank them and break the ties. And this taxonomy in the paper is very strict because it's only used for break ties. But in your real world system, you might have other refinements. It doesn't have to be just break ties. You can reorder them. You can, like, I don't know, remove some of the candidates if you don't like them. So the whole point takeaway here is if you have multiple ones and you want to have a hierarchical structure, you will need to identify the strong recommendation system, use it as a primary one, use the secondary one to refine the result. Okay, so next one, meta-level hybrid. So, okay, so this one is very similar to the augmentation, but I will show you how this is different. You first use a model learned by a recommendation system and use the result as the input to another recommendation system. This is very similar to the feature recommendation, feature augmentation hybrid. The difference is that in the hybrid level, in the meta level hybrid, your contributing recommendation system will completely replace the original knowledge source with a learned model. And what does this mean? A very simple example. Let's say you are building a recommendation system and you are using you have a very cool machine learning model. Let's just call it ML. Based on the machine learning model, the machine learning model takes input for people's description. And the machine learning model will be able to classify this person. This is probably not ethical, you classify personality, but you classify this person, each person's personality into 3 categories: A category, B category, and C category. Okay. Then in your recommendation system, you will base on the personality. You say, all right, the input to the recommendation system is now A personality. What would be the movie that A personality like? Then you make the recommendation. Okay. And what you can see here is your original data, either ratings or descriptions of this person, are completely gone. You are not using them in your recommendation system. You only use them in this machine learning model to be able to determine the personality type of this user, and then based on the type to make recommendation. So this is why it's called meta level, because you're looking at this meta level. For augmentation, you are still using some of the original data, right? So you're augmenting this sparse matrix. You still have some ratings are from the original raw data. If we look at one example here, The term collaborative through content refer to a restaurant recommendation system use a naive-based technique. This is machine learning technique to build models of user preferences in a content-based way. So with each users are represented, the collaborative filtering then performed on the vectors compare peer users identified, right? So you first have a model, and this model will represent the user in some space, right? Now you completely remove the original user data, like what we did for personality A, personality B, and personality C. And then you use these meta features for your real recommendation. And it works like this. So again, you have some user profile, contributing recommender will generate personality, like the candidates, what is called candidates. Then you take candidates and send it to the actual recommendation system and generate a score. So to understand this figure, please read the paper, but it's actually very simple. This one will generate some meta feature to describe your user or items, and this one is going to make the final recommendation based on the output from here. They have the overall score. All right, so for your homework 3, you should take a look at the collaborative filtering. So it doesn't have to be 2.2.0, you can just look at the latest one, because Spark ML do have this collaborative filtering method built in. So there is a question, do you have a link for the paper? I think the link is at the first page of the slides. And also I want you to read this paper, because this paper tells you how to evaluate a recommendation system, the metrics, the criteria, and all that. So today in these slides, you have 2 papers you have to read. They will be in your quizzes and your exam. One is the survey paper for hybrid recommendation system. The second one is the evaluation. Yeah. Okay. And start to think about how you will be able to improve your homework 3 if you already finished your homework 3. All right, so great. And now we are going to go to the graph lecture. I'm very excited. Now we are done with your recommendation system, and you can all start building your recommendation system for your homework 3. So how many of you have started your homework 3? No? Okay, cool. All right, test one. Okay, great. And okay, recommendation system. Your TA is going to release your homework 4 very soon. But you still have time to work on your homework 3 before homework 4 is due. There is, I think, 1 or 2 weeks overlaps, and I do this because I just want to give you the opportunity to better manage your time, because I know some students did the homework 3 very quickly. In previous semesters, we have students finish assignment 2 in like 2 days, and they want more assignments. But we don't want to add too much assignment. I think we are at the right level right now. So let's take a 10 minutes break. Once we come back, we will start talk about graph and social networks. If you have any questions, put them in the chat. I will answer them when I come back. All right, I'm back. Social networks here. Okay, so this week's no, not this week. Today and next week, and maybe the week after, we are going to cover social networks. This is a very cool example of different types of data that we can process in data mining. So far we talk about what kind of data in your market basket analysis frequent item set. We have market and basket, right? You have items as set. Then in finding similarity, similar documents, you have this metrics, you have documents and features, again, data points in the matrix form. In recommendation system, again, we are looking at metrics, right? But some type of data are can be easily represented using a graph. So in this lecture, we are going to look at different methods to mine graph data. And one major application is social network data. So let's look at them. All right, so we often think of networks being organized into some modules, or you can call them cluster or communities. If you look at here, each color represent a community. Right, so for example, each node here could be a person, and each link represent friendship. Right, that's the easiest way you can think of social networks in a graph representation. But you can also think about other examples. Each of this could be a sensor, right? Traffic sensor, and each link is the road distance between two sensors. What would be other examples of a graph? We talk about friendship, we talk about sensors. Anybody? Any examples of data that you want to represent them as a graph? No one? Yeah, distance could be the link between nodes, right? So, but what would be your nodes? Knowledge graph, yeah, knowledge graph is a type of graph. Or you can think of this as maybe each node represent a company, and a link between company is the correlation between their stock price over maybe last 5 years, right? Then you can look at, you can try to identify communities together. This will be a bunch of companies that their stock price have very strong correlations. Okay, distribution centers will be node, and you have links that are road distance word co-occurrence. Okay, yeah, that's a good one. So each node is a word, and co-occurrence would be the link, right? So link would have weight. So you can have strong co-occurrence, or you can have weak co-occurrence. So this is just to let you know that given all these examples, to first let you know that many things can be represented as graphs. And we're going to focus mainly on social networks because it's easier to explain, but don't limit yourself in social networks. Our goal to migraph data, okay, so paper co-authorship, that's a good one. So each node would be an author, and each link would be, if you have a link, means these two people have co-authored a paper, right? And then you have some semantics about the clusters. So our goal in the lecture today, there are many different types of graph mining techniques, but our goal here is to identify densely linked clusters in a graph. So densely linked clusters does not mean you have a cluster with many nodes. It means you have individual clusters here. Each of them within clusters, you have many links to connect all the nodes within the cluster. Right? If you look at this between these two clusters, you only have 3 links between these two, this one, and this one. You only have 3, and so on. So here you can easily see some graph structure and some densely linked nodes. And this type of clusters can be very useful. So just remember, we are always looking for densely linked clusters. So this is coming with us for the entire graph lecture. Okay, so why is this useful? If you look at graph data from social networks, could be Twitter, could be from Twitter, could be from Facebook, you will be able to discover social circles, circles of trust. For example, this is you. You have links to other nodes. If we can identify clusters, maybe there will be one cluster that represent your family members, another cluster represent your high school friends, another cluster represent your college friends. And something interesting here is these two clusters have overlaps, and these two nodes both belong to your high school friends, also your college friends, right? And within your college friends, you also have a small, even more densely linked cluster. This could be your computer science friend, and an even smaller one would be all the friends with the same under the same advisor, right? If you think about each node, if you think of each node as a person, each link represents the strength of your interaction. In your CS department, within your CS department friends, the friends under the same advisor will be the people that you usually interact with, right? So you have very strong links between them. Okay, so this is some application that we can do if we can find clusters in a large graph. So we are then going to talk about community detection. We're going to talk about algorithms to do that. And most importantly, we are going to work on undirected and unweighted networks. So this is the simplest one. There are other algorithms that will be able to work on directed graph or weighted graph, but not before you understand how we can process undirected and unweighted graph. So what does it mean undirected? So if you have 2 nodes in a graph, your link can be this, right? This is undirected. You don't have direction. Or you can have a direction like this. So for friendship, this is a good way to represent it because friendship doesn't really have a direction. For other types of data, you might want to use this. For example, say traffic sensor. You can say the traffic flow is from this sensor to this sensor, so you have a direction here. Okay. And for weight, for friendship, you either have a friendship one, which means you have an edge between these 2 nodes, or you don't have a friendship, which means you do not have an edge between the 2 nodes. It will be a 0. A weighted network, this weight can represent, for example, if this is traffic sensor, we can represent a typical traffic volume on this route, right? So it can be 10, 10 of some unit, right? Just have a weight on that edge. Okay, all right. So the ultimate question that we want to answer is how do we find communities in a graph, especially when you have a large graph with many, many nodes and many, many links. So the first algorithm we are going to talk about is using this betweenness concept. This is your task 2 in your assignment 4. So betweenness concept is very simple. You calculate something called an edge betweenness. This is a score for an edge. And the definition of this score is the number of shortest paths passing over the edge. So if you look at the graph here, what does it mean, number of shortest paths? So how do we generate shortest path? Well, there's many many algorithms that you can use and heuristics that will be able to speed up the process. But let's just think about what would be the requirement for you to generate shortest path. When we are talking a path, you require how many nodes? Well, at least the starting nodes and end nodes, right? So if we look at this graph, you have 1, 2, 3, 4, 5, 6, 7, 8. You have 8 nodes. And if we take 8 nodes, pick 2, this is the combination. This is the number of pairs of nodes that you can have to calculate the shortest path, right? One for start, one for the end. So let's say this one is start, this one is end. Your shortest path will be this. Okay. And if you do this, that means, well, if you do this, the shortest path is this one. That means this edge has now one shortest path passing through this particular edge. And if we look at another example, let's say this is your starting node, this is your end node. The shortest path will be what? Here and here, right? Now you start to increment the number of edges on each number of shortest paths on each edge. So this one, this one. And let's say the third example, start from here and here. Shortest path, this, and this. You update the shortest path number 1. Now this becomes 2 because now you have 2 shortest paths passing through it and 2. Okay, so the betweenness score is just this number once you go through all possible pairs as the starting point and the destination endpoint of your shortest path, right? So you start from this one to every other node in the graph, then you start from this one to every other node in the graph, and you accumulate all these numbers. So the interesting thing about betweenness is if you have a high score, that means many shortest path has to go through you. Then this will be the link that we can use to identify the community. One example is the Russian bridge. The Russian bridge is here. So you have people live in this part of the world and this part of the world. Think about when you are calculating pairwise shortest distance between this entire graph. If your starting point is here, end point is somewhere within this island, your shortest path will be somewhere here, right? So many shortest paths here. But if you start here and you end here, your shortest path has to pass through what? Well, the Russian bridge. If you start here and end here, your shortest path will have to pass through, again, the Russian bridge. So the Russian bridge will be used many times for traveling between these two groups of areas, right? So you can expect that your Russian bridge will have a high betweenness numbers. And this is the entire idea of this betweenness concept. So if we can find edges in a social network graph that are at least likely to be inside, our goal is to find edges in a social network graph that are least likely to be inside a community, right? That's the one with a high betweenness number, your Russian bridge. So, well, we are going to look at one more example, but let's just look at the definition. Formal definition of the betweenness. Betweenness number, the betweenness score of an edge AB, is the number of pairs of nodes X and Y, where you have X and Y belongs to your graph C. This AB lies on the shortest path between X and Y. If there are several shortest paths between X and Y, you will credit AB with a fraction of the shortest path that includes edge AB. Okay, just on hold. I know this might be confusing, but let me tell you, if you are here and you have a Russian bridge, you have a Russian bridge number 2 and 1. So from here to here, you can either use 2 or use 1. They give you the same shortest path, okay? And in this case, you will need to credit half of the shortest path to Russian bridge 1, half to Russian bridge 2, just to be fair. Just to say, okay, if someone randomly choose the shortest path, 50% of the chance it will be going through Russian bridge 2, 50% of the chance it will go through Russian bridge 1. So that's here, fraction of the shortest path. That includes edge AB. And we're going to see one example on how to calculate this. So don't worry if you don't understand it now. A high score is bad. That means many shortest paths has to use this edge, just like our Russian bridge. And this also implies A and B are in different communities. If we look at one more example here, this is your graph. What would be the community that you think you will be able to identify? Well, okay, take one step back. What's the definition of a community? What exactly are we looking for? So someone say A, B, C, and D, E, G, F. So why A, B, C, and D, E, G, F? What's the property of the cluster that we are looking for? Okay, so one answer is the link. There's one link divided to community. Okay, which is fine, but what makes it a community? We talk about this at the beginning of the lecture. A community means, okay, so Luke said multiple connections between nodes within it. Okay, very close. So you're good. A community or cluster means within the cluster, all the nodes are densely linked, right? So multiple connections between nodes, right? If we look at this, this is ideal, right? Within each community, it's a strongly connected graph. Every pairs of nodes are connected. So think about this. If you just include D, this is less connected, right? Because D in this community only connect to B, but not A and not C directly. So we don't want it. If we add these two edges, it becomes a good connection. Sorry. If we add this, okay, let me do this. So you guys are saying that we have one community here, we have another community here, right? Great. What if I add one more edge here and add one more edge here? What would be the communities that you can identify or you want to identify? Remember, the definition of a community or a cluster is densely linked nodes. What would be your answer? Anybody? A, B, C, D, and D, E, F, G. Okay, great. Yes. A, B, C, D can be in one community. D, E, F, G can be in another community. Okay, very good. So this is great. So you guys now understand the concept of what you want to identify, right? So now we are going to talk about technologies, that algorithms that can help you to identify them. But in this case, D is in both community, yes. But some algorithms will not be able to do this. Some algorithms will not be able to identify overlapping communities, and we just randomly assign D to either one of the community. Okay, so we can worry about this later, but I want to make sure that you guys understand what you are looking for in the graph. Okay, so we expect this BD would have the highest betweenness because we want to cut here. to form two communities. So BD is on every shortest path from ABC to DEFG, right? If you want to go from here to here, you have to pass BD. So the betweenness of a BD, if we only consider this part, it would be 3 times 4, 12. The F is on every shortest path from ABCD to F, right? A, B, C, D. If you want to access F, you have to use the F. The betweenness of the F will be 4 times 1, will be 4. And natural community will be ABC and DFG. So this is just to compare these two numbers to show you that, okay, 12 is really large compared to this one. So this one will be the highest one, and we want to cut it here to form two communities. So far, I show you the desired output, the output that we are looking for, densely connected nodes. And I show you this concept of betweenness. But the real question is, how do we compute the betweenness? And how do we select the number of clusters? I think we will be able to finish this today. So that's the Gervin-Newman algorithm. The Gervin-Newman algorithm helps us to discover communities, use some hierarchical clustering approach. It's a top-down approach, which means you start with one cluster, that's the entire social network, and we recursively split the cluster into smaller communities. We do this based on the notion of the betweenness. We do this split based on the notion of the betweenness, which is the number of shortest paths passing through the edges. Here's the algorithm. You start by looking at each node. You compute the number of shortest paths from each node to each of the other nodes that go through the edge, just like what we did in the example. Then you repeat the process to calculate the betweenness of each edge. Once you have the final betweenness number for each edge, you use a threshold to remove the high betweenness edges because you think these are between community edges. You remove edges, or you can remove edges with the highest betweenness. This is the between communities. Once you can do this, you start to remove edges. The remaining connected components are your communities. Then you can repeat calculating the shortest path. Use the shortest path to calculate the betweenness. Remove the highest betweenness. You have more communities, and this will be a hierarchical structure. We're going to look at how we do this later, but this is the general outline of the algorithm. Okay, so for the Gervin-Newman algorithm, you visit each node X once, compute the number of shortest paths, right? Like what we did. So how do we do this? Here are the steps. Give me 1 minute. All right, I'm back. So how do we really calculate the betweenness numbers? Well, we do a breadth first BFS, breadth first search of the graph, starting at node X. So you should know how to do this. I think this should be in your data structure or algorithm course. And because we are doing the BFS, the level of each node in the BFS is the length of the shortest path from X to a particular node. we're going to see one example next, but let me just go through the steps here. So the edges that go between the nodes on the same level will never be a part of a shortest path. You can ignore it, right? Because you're doing a breadth first search. Edges between levels are called the DAG. DAG edges directed acyclic graph. Each DAG edge is a part of at least one shortest path from root X to some node. It looks like this. This is your original graph. If we start by taking E as the root, you're going to do this with every node as the root. You just repeat on every node. Using E as the root, then when you are construct the breadth first tree, E, D, and E, F, right? So D, F, and from D can go to G and B. So B and G. From F, you can go to G, F go to G. F can also go to D, but do we want to include D in the tree? We do not, because D is already in the tree. That's that's within level. You don't want to include within level because this link is never going to be in any of the shortest paths. Okay, so once you can construct this tree until you have what, A and C here, then you can start to calculate the number of shortest paths that you would have from E to a particular node. For example, from E to F, there's only one path. E to D, there's one path. So Peter is asking, what are the ones and twos? Okay, so I'm explaining this now. So from E to F, you have one. From E to D, you have one path. From E to G, how many paths would you have? Shortest path. E, D, G, so 1. E, F, G, 1. So 1 plus 1 is 2. So this is to tell you that from the root node as the starting point, G as the ending point, there are 2 shortest paths of the same length. Okay. What about B? So E to B, 1 path. What about A? 1 path. C, 1 path. Okay, cool. So based on the tree, if you just traverse the tree, you will be able to generate all these numbers, and these numbers tells you the number of shortest path from the root node to you. Okay, you have an E here. This is for E itself. Okay, so once you can generate all this number, you put it aside. You just keep a record on how many shortest paths you will be able to generate from the root node to this particular node. Then we are going to calculate the betweenness. So to calculate the betweenness, you start by labeling each of the leaf node with a 1. So on your textbook and on the slides, it doesn't really tell you why do we want to label this 1. But think about this 1 as in a similar way as your FP growth algorithm. This 1 indicate there is shortest paths of one particular length. Okay, I'm not very good at writing. There are shortest paths, one shortest path or multiple shortest path of one particular length from E to G. So for example, from E to G, you have 2 shortest paths, but they have the same length too, right? So you have a 1 here, you have a 1 here, you have a 1 here. Everybody has a 1. Then from this 1, you start to propagate. You say, okay, there's one length and this path has to go through here. So 1. This path to reach C, it has to go through here. 1. Right? And if you look at B, the shortest path that would reach B would originally be will have a 1, but plus this 1 plus 1 plus 1 becomes 3. And this 3 says at the node B, the types of shortest path that will pass through B or end at B will be 3. Then you just take the number here and you keep going. So the slides shows you how to do it here. You start by crediting your leaf nodes, say A and C, you give credit of 1. Each of the node has one parent, so the credit is directly going to the edge BA and BC1, okay? So you should start to see this because from E to A is this path. And it tells you that, okay, there's one particular type of shortest path that will end at A, right, from E to A. And this path has to use this thing. So you have a 1. And this is directly propagate from here. The same goes for C and BC. At level 2, we start to look at level 2. G is the leaf node, so it has a 1. However, if you look at B, B is not a leaf node, so which means there are shortest paths that will go past B to reach other nodes, right? So how many shortest paths are there? We can look at the edges below B, but connected to B, so 2. Plus 1 for B itself, so 1 plus 1 plus 1 equal to 3. Okay, so B gets credited 1 as you would credit A, C, and G. So now B is 3. What about the edge BD? B has only one parent, so 3 is here. That means if 3 shortest paths ends at B, and to get to B, you have to go through DB, so this between this number will be 3. If you look at G, G has 2 parents. So how do we divide this credit of 1? Well, very simple. You just do 0.5 and 0.5 here. Right, because there's one shortest path, one shortest path. They both have the same length because they are shortest paths. But the probability of choosing either one is the same. So how do we calculate that? Formally, to calculate for an edge E, it will be the sum over all nodes of the shortest paths from the root X to Y that will have to go through E. Compute the sum of nodes and edges starting from the bottom of the graph, like what we did for all these ones and going up. Each node, other than the root node, is given a credit of 1. This just says that there is a type of shortest path that will end at U, right? You will be the destination at least once. Well, exactly once. Each leaf node in the DAG get a credit of 1 to start. Each node that is not a leaf node gets a credit 1, plus the sum of credits of the DAG edges from the node to the level below, right? Those are all the shortest paths that have to go through this node. A DAGE enter the node Z is given a share of the credit proportional to the fraction of the shortest path. That's for G. We're going to look at this on the next slides. Yeah. So in the case of processing, propagating DG and FG, we can look at both D and F. So from D and F, both of them have just one path from E to G, right? So you do this 1, you do this 1. Sometimes you might have multiple, let's say 3 here and 1 here. Then you have to weight them differently. But in this case, you have 1 and 1. So in this case, you are going to have credit of node G to each of those edges. So 1 divided by 2 will be 0.5. So dg will be 0.5, fg will be 0.5. So in the cases that this is not evenly distributed is here. So generally, the way you distribute credit of a node to its edges depends on the number of shortest paths coming from different sides. Say there were 5 shortest paths to D and then to G, and only 3 to F, then to G. The way you distribute the credit will be for DG will be 5/8, for FG will be 3/8, right? This is pretty straightforward, because if the chance of picking the shortest path is equal, then the probability of picking DG will be 8 divided by 5, because you have 5 shortest paths that will go through D. And for the FG will be 3/8, because only 3 goes to F. Okay, great. So node D gets a credit 1 plus all the credits below it. So 1 plus 3 plus 0.5. What is the 3 here? We're talking about node D. And that 3 is for node B. Great. So this is here, right? This means if you want to reach this edge from E, you have to pass through D, right? So 1 is from D itself, 3 is from BD, 0.5 is from DG. For node F, it will get credit for 1, this is itself, and 0.5, this is for edge FG, so 1.5. D has only one parent, so HED gets credit for 0.5 from D. And you can do the same thing, it will get 1.5 from F. So that's it. That's the way you calculate the betweenness. So remember at the beginning of calculating this, I think someone asked a question, what are the 1s and 2, right? 1s and 2. This is the number of shortest paths, which you can use when you are distributing the fractions. But when you are propagating the values, you are not really using that numbers. Okay, so this is your final result when you pick E as the root. And the numbers on the node is not important, because you only care about the betweenness at each edge. So awesome, right? Very simple. And once you do this, to complete your betweenness calculation, you need to repeat this process for every node as root. We only show you that using E as the root. Then you sum the contribution on each edge for each run. Okay, so here, each run. You divide it by 2 to get the true betweenness, because each shortest path will be counted twice, once for each of the endpoint. Let me just come back to the tree here. So now you take E and you build a tree, you generate a betweenness, every edge has a number, right? Then next time when you run this, you take F as the root, so it will be F, E, G, and D, and so on, right? Then you use this tree to calculate the betweenness number again, and the edge of EF will have a betweenness number, and remember here, you have a betweenness number, so you're going to sum this up. However, like in this example, this betweenness is calculated twice. Once when you have E as the root node, F as the endpoint of your shortest path. The second time is from F to E. So eventually, after you calculated everything, use every node as the root node, you have to divide it by 2, because every shortest path is counted twice. Okay, so betweenness scores for edges for a graph behave something like a distance matrix, but it's really not really a distance matrix. You could cluster by taking edges in some increasing order of betweenness and start to generate communities. For the Gervin-Newman approach, once you generate the betweenness of the numbers, betweenness of each edge, you start with a graph and all the edges, remove the edges with the highest betweenness number. You continue until your graph is broken down to some suitable numbers of connected components, and you are done. This is top-down hierarchical clustering, divisive, and I'm going to show you some examples right here. All right, in this case, let's say we have calculated all the betweenness numbers. Now your BD has the highest betweenness number, 12. We can remove the edge BD. It will give us really nice communities, right? ABC and DEFG. So are we done yet? Well, you can say if you only want 2 communities, you're done. But you can keep working on this. You could continue to remove edges with the highest betweenness number. Let's come back here. What would be the highest one? 5. Right? Now, how many communities would you have? 1, 2, 3. And you can go further. You can say, I want to remove high one, remove this one and this one. So the left side is the same, but the right side, you are dividing this large community into, oh, no, it's still connected, right? D and F are connected, E and F are connected, G and F are connected. So it doesn't really change your community structure. So you go one step further, you say remove 4. Now you remove this one. This means D becomes its own community, G, F, E becomes its community, right? And you can keep doing this, and eventually every node is one community. It's a top-down approach. So you can continue to remove edges with the highest betweenness. Why would you want to do this? Oh, because many times you want to find community structures within a community. Like in the previous example, you can identify community, say computer science friends, right? You take the computer science friends, you want to find sub-communities. Maybe you have closer friends in computer science and others. Does that make sense? Okay, cool. All right, so here I'm going to show you how you would run this Gervin-Newman approach. Recall that we are going to run this divisive hierarchical clustering approach based on the notion of betweenness. You start with undirected, unweighted networks. You repeat until no edges are left. You calculate the betweenness of the edges. You remove the edges with the highest number. You can recalculate the betweenness again. You don't have to. I'm going to talk about the pros and cons of this. Okay, so start. The connected components in your graph are communities. So assuming that at the beginning, everything is connected, so you have one component. And eventually, if you are using this divisive hierarchical clustering approach, each node will become its own community. And this gives you a nice hierarchical structure of the network. So the example is here. This is your original network. You compute the betweenness. All right, say this is the highest betweenness number. Remove it. You have 2 communities. Awesome, right? So now you have 2 communities. This is your family. This is your school friends. And say you want to find, maybe there are communities within the school, within your school friends community and communities within your family community. What you can do is you run the betweenness numbers again. right? So because you already cut it, so the betweenness numbers would change. Well, depends on how many edges you cut. You have cut it. The betweenness number might not change that much, but you can recalculate them again. And again, within each community, you cut the edges with the highest number, and this is your result. You do this again, and this is your final result, right? Each node is a community. And this gives you a very nice hierarchical structure. This is a family cluster, school cluster. Within a family, this is probably your dad's side family. This is your mom's side family. With school friends, this is probably friends from the same department. This is the friends from the same club, right? And you can keep doing this and find more interesting structure in your data. Oh, and people has been working on studying this publication records. This is some results in physics. Collaborations could be two people working on the same similar topics. They have a link because they were on a paper before or on a certain number of papers before. And some interesting social science, this Zachary's Karate Club, I think you can still find the data set. A long time ago, I think it's in the 80s, a social scientist tracked this Zachary's Karate Club. And the idea is to build all these links if two members in the karate clubs or parents of kids that are in this karate club, if they talk to each other very often, you're going to have a link. And using this social network analysis, this has very small data set, probably 34, 35. They identified two center hub to communities and two hubs of the community. I think one of them is the coach. I don't know if you could tell us. Well, I don't know if the instructor in the karate club is still called coach, but the coach. And the other one is the head of the parent association committee of the karate club. And they, based on this social network, they predict that if the karate club is going to break into two pieces, this will be the way to divide the club, because here it's densely connected, here it's densely connected. And I think in their original paper, this actually happened. The karate club is divided into two parts, and their original guess hypothesis was pretty accurate. And you can see the dendrogram here, right? So at the beginning, everyone belongs to the same cluster. So you have only one cluster. At the end, each node is a cluster. And if you cut somewhere, you will be able to form this hierarchical clustering settings. All right, so that is it for today. And I'm going to host my office hours now. If you have any questions, please come to my office hours. If you don't have any questions, I will see you on Monday. Please work on your homework assignments. And more importantly, please read your textbook, read the paper. Have a nice weekend. Enjoy the really nice winter storm and rain in Los Angeles. Just be careful if you are driving. All right. Thank you, everybody. I will see you next week. And for the people who wants to come to the office hours, give me 2 minutes. I'll be right back. All right, I'm back. Any questions?
Can I start first?
Sure.
Hi, Professor. I actually want to retrieve back a little bit to the LSH because I was restudying the Minhash and LSH for the
Sure.
homework.
Sure.
And I'm confused about the connection between Minhash and LSH. Like under, like why do we have to use LSH? Because I
Oh,
think
oh,
I
you're using LSH because you don't want to compare every possible pair.
because I don't want to compare every possible pairs.
Right.
So for
Uh,
example,
okay. So what's the example?
I generate the main hash table, which is all the user ID for the columns, and the rows are, for example, 50 hash functions, right?
Okay.
And then
Yes.
how am I gonna do to do the LSH? Like like
You divide the
sample?
right. You divide them into bands.
Yeah, and I divide them into bands and I sample the bands again.
You don't sample, right? You compare each band.
But on the
Oh,
last,
oh, okay. Yeah. So let me do this. Let me do it on the whiteboard.
yeah, thank you very much.
Sure. Sure. We did talk about this, but I know this can be confusing.
Yeah, because today I was watching the lecture slide, the lectures recordings.
Okay, so let's say you have your document. You have your document, D0 to D1 median, and you have your hash function, hash1, hash2, hash3, and so on. Say you have 60 hashes, and your band is your R equal to 3, your B equal to 20. So if you are not going to use LSH, that means to compare the similarity between D0 and D1, you have to compare each symbol,
Yes.
right? 60 times, right? You have to do 60 comparisons.
Yep.
Are we good?
Yeah.
So in LSH, what the slides doesn't really tell you is you take this, I think we did this on the whiteboard.
Yes.
You did this, you take a hash function and you generate a number to represent it. Because you treat this part, you treat this part and this part as a string, right? So the hash function will return you a number. Let's say that number will be between 1 to 1 million. Just make sure that, oh,
Can I
just
stop
make,
you for a little bit?
sure.
I think you did multiple examples on the whiteboard, and there was one like what you just said, hashing the function into a number, and
Right,
you also said this is no collision. But
right. There's no collision.
in another whiteboard later on, for sampling the band, you did another example comparing those numbers, for example, 021, 012, something like that.
Right.
And
So, yes.
what is the difference between the single number and those a setup number?
Okay. Okay. So if you think about what we talk about on the slides,
Yep.
that tells you that if D1 is a candidate, at least one band has to be identical.
Yes,
right?
correct.
And how do you know there is at least one band that's identical? You
Um,
have to compare this, right?
Yes.
So eventually you will have to do 60 comparison
Yep.
to figure out, to answer the question that if there is one band that's identical.
Yes.
Then it will be exactly the same like without LSH, right? The
Okay.
same processing steps.
Okay.
But the slides only tells you that, okay, if the contents are identical, because it's only talking about concept. If the contents are identical, it's a candidate. But if you really think about it, when you implement it, to find if there is one band between the two documents are identical, at least one, you have to compare every band. You cannot say I only want to compare the first couple ones and I just ignore the last one, because what if the last one are identical, right? So if you are doing this, then you are exactly doing 60 comparisons, component wise. This will be exactly the same like
Or
without LSH.
yeah, you have to do 60 times for comparing one min hash, one signature.
Right, right, right. So just to be able to identify if these two are candidates, if D1 is a candidate for D0. So this is not okay. The concept is comparing the content, but in practice, how do you compare the content more efficiently? Well, the idea is you can hash this into a number and then you just compare the number, right? So for each band, you only compare once because you
So,
can pre-generate all the hashes.
so what is the input of the hash function this time?
The string here.
The string. The string or the signature?
Signatures are strings. So,
Okay.
right? So if you have signatures 1, 2, 4, then the string is 1, 2, 4.
Okay. Yeah, yeah. I get that.
So maybe let me just try this again.
Yeah, because sometimes you draw on the whiteboard in the transpose of this matrix, and sometimes you draw it like this.
Yeah, I think that's very cool because it helps you to really understand the algorithm. If I always do it the same way,
Yeah, so I have to like
and
do it vertically and horizontally over and over
yeah,
again to
yeah, I know.
think about it.
Yeah, just to train you. So next time, whatever metrics people throw at you, you'll be able to come up with the answer. So
Yeah.
let me do this again. Let's say I have 60 signatures, right? To compare this to D0 and D1, the worst case, well, not the worst case. Without LSH, I have to do 60 comparisons, right? Between signature comparisons.
Yeah.
And if we have LSH, divide them into band, to be able to answer that question, that we have at least one band that are the same, at least one band that are the same.
Yeah, this is something similar to the PCY.
Right. But in this case, the worst case, you have to do 60 comparisons, right? You might get lucky when the first, let's say if the first band are identical, you only have to compare 3 times. But the worst case, computer science usually often just talk about worst case. In the worst case scenario, you have to compare 60 times.
Yeah.
So to improve this, you can take this string of signatures and hash them, and you have one number here instead of a long string, and then you just compare that number. So instead of comparing 60 times, if you have a band R equal to 3, now you compare, worst case, you compare 20 times.
Okay, yeah, that makes sense. Yep.
Okay, cool. Any other questions?
So the main idea of the LSH is just to cut the whole to cut 60 hash functions into like 3 or 5 sections, and then use only one hash function to hash into the chunk, right? The chunk, for example, D0 and min hash 1, min hash 2, min hash 3, and then you generate a value, a output, like for example, a single like 5. And then you
Yes.
compare the other value in D1 to see if they are identical.
Right.
Okay, I get it. And I'll keep trying that later on. Thank you very much.
Sure.
Can I have a question following this?
Sure.
Hello, Professor. Well, I think during lecture, the main idea of LSH is we don't want to compare each of the documents. But looks like here, the LSH just save us the compare time between two documents. Well,
Yeah, so I think more accurately, we do not want to compare every possible pair entirely, right? You don't want to do 60 times for every pair, but you still have to do some comparison. You cannot really skip any pairs.
well, what I mean is LSH, we want to save the compare between different documents. That's why we want to have the candidates.
Right.
But that means we want to save the, I cannot make annotation. That means we want to save the comparison between the rows.
Right.
But here it looks like we are focusing on one pair. For example, D0 and D1, and we save the comparison on columns. Do you think that is contradict idea?
Oh, okay. So when we are saying that we don't want to compare two pairs. Oh, somehow. When we say we do not want to compare, let me see, how do I share again? when we say we don't want to compare them, we mean, we don't want to compare them entirely. We don't want to compare all 60. We only want to compare
Right.
some of their.
That's within the one pair, right? That's within
Right.
one, two documents.
Right. So for the next document, you still need to compare some of them to be able to say if you want to compare them entirely. Because remember, at the end, you still need to go back either to the signature or to the raw data you have to go back to the raw data to have the exact, to have the real Jaccard similarity. Yeah.
Right. So it looks like the LSH does not really save the comparison between the number of comparison between documents, because you still have to compare each of the
yes,
pairs.
Right. More accurately, you still have to compare each pair, but you can do partial comparison if you call them partial comparison.
Well, I feel that contradicts the idea when we're talking about at the beginning that we say mean hashing help us to reduce the columns, and the LSH help us to reduce the comparison on rows.
But think about this, you don't have to, many rows now, you don't have to compare their original data, right? If their signature and their band does not put them into the same bin, then you don't have to compare their raw data. But I think you understand the approach. This is more like a semantic question, right?
Right. If they are not a candidate, then we don't have to compare their real Jaccard similarity. Oh, right. In that case, right, it saves the comparison.
Yeah.
Yeah. Yes. Thank you.
Sure.
Hi, Professor.
Yes.
I still have a very quick question. So in the slide similar items on -1, page 96, yeah, that is exactly right after we have found the candidate pairs. So
do you want to share the slides so that I can see?
Yeah.
You can just override my sharing.
Okay.
How's everyone doing in the class? Still hanging there?
No, not really. I got lost every time, and I just rewatch the recordings.
That's okay. If you are still rewatching the recording, that means you still are learning. So that's good.
Yeah. For example, in this step, examine signatures of candidate to see if the fraction of common rows.
Construct the candidate pairs. Yeah, so this is just look at signatures, right? You use the signatures to estimate the Jaccard similarity.
Okay, so we just calculate the Jaccard similarity and
based on the signature.
And to filter out those so-called real similar pairs.
Right, but you can skip that step, right? So you can also skip this step. You just check the original document because it says may check. Sometimes you stop here because if you think your signature give you good enough estimate, you just stop. Sometimes you really want to go to the real original feature to check them.
But how do I know my signatures are giving good estimates?
Remember, every time I have someone has a question similar to this, how do I know which one I want to use? What would be my answer? You take a small data set and you test it. So every application is different. There is no fixed way to do this in data mining, especially when you're tackling large data set. Right, so like, how do you know if you want to use Pearson correlation or cosine similarity? You take some small data set, you test it,
Okay.
then you see if you really want to do this, right? How do you know you want to use 50 signature or 100 signatures? You take some small data set and you test them.
So I might just hard code some small set and do the testing. I see.
Yeah, empirically, you will be able to find a good way to do this.
I see. Appreciate that. Thank you very much.
Sure. All right, anybody else?
Hello, Professor. I have some questions about this course.
This course, you mean the question about the topic in this course or the course in general?
No, the social network.
Oh, okay.
Sorry, the social network part. Yeah. And the first question is that could you mention again how to calculate the betweenness? Or like BD, is that how to get 3 times 4?
Oh, don't worry about this. I should say this. Don't worry about this. This is just some random example to show you that this could be done and to show you that BD is 12, DF is 4. But I don't think this is true. Because this is saying that BD is on every shortest path from here to here, right? So the number of shortest path from this side to this side is 12 because you have 3, you have 4 here, so at least you have 3 times 4, so it would be 12. But don't worry about these numbers.
Oh, okay. Will you mention more detail the next week or?
Yeah, I would just tell people don't worry about these numbers.
Okay.
This is made up numbers. Yeah.
Okay, got it. And the next question is about the so for this graph, we suppose that the start point is E, right?
Right.
Okay, and so G there is 2 because there are 2 same shortest paths that pass through the G.
Arrive at G, and 2 shortest paths of the same length.
So like EDG and the EFG, there are
Right.
the 2 paths are same. Okay, and after we drew this graph, and we need to drew this one.
Right.
So could you go over again of the steps to how to do this graph?
No, you can watch the video.
Oh,
if I
okay,
want to go do this again, you can watch the
sorry.
video, right? But if you have a specific question, I can help you.
Yeah. After I finish after I finish this graph, so how to like divide the clusters? Like we have the
You just
yeah.
you this is just one tree, right? You have to do this for every tree, starting from root node as every node. Then you combine them, you divide, then you remove the link with the largest number.
Like from E and ED is the largest number 4.5.
No, this is only one tree, right? You have to do this for every tree.
Every tree means that we need to change the starting point.
Right, you are correct.
So we need to do maybe 7 times.
1,
because
2,
there are 7
3, 4,
points.
5, 6, 7. Yes, 7 times.
Okay. And next one. Actually, I do not make a connection between this graph and this one.
This is just a tree. The tree is helping you to calculate the betweenness. The graph you're seeing on the next few slides is after you calculated all the betweenness numbers.
Oh.
You probably will not be able to understand how to do this unless you do it. But don't worry, next week, the quiz. Oh, I forget. This will be on the quiz. can you also help to? Did you do it last time, or was that you?
Yeah, it's me. It
Okay,
was me.
yeah. Can you do this again? I'll ask you guys to calculate the betweenness numbers for an edge in the graph.
What?
You can tell
could you-
people. You can post on please post on PS to tell people.
Actually, I want to make sure which graph we need will be increased. Is this page or
This is a tree, not a graph.
graph? This page.
So
Because actually I'm a little bit confused about the graph and the tree. So
oh, the tree is derived from the graph, right? So you take a node from the graph and you do a BFS, then you generate a tree. Do you know what BFS is?
let me. Oh, I did not find B.
It's not on the slides. It's a prerequisite.
This one.
Yes.
What is BFS?
It's breadth first search. But okay, that's your homework. You need to read about BFS and how to generate them.
Okay. Which part will be in the quiz?
Okay, yeah, you're the professional quiz reminder. Someone said that in the quiz. Chen Yuan.
So which one will be the quiz? This part or the graph? Because this is the first time I know that, so I.
Okay, so go read about BFS and how to generate them from a graph. And I can tell you, I will test, the quiz will contain a question that asks you to calculate the betweenness of one or multiple edges in a graph, not a tree.
So this is the graph, right?
This is the graph, right?
Oh. And will this number are made up number or the true number?
I believe these are the true numbers, but I never really calculated it. You should do it and see if they are the true numbers.
Okay.
Exercises on the textbook will be the true numbers.
Okay. Which chapter will include the social network in the book?
It's on the
Which chapter?
syllabus. I don't
Okay.
really remember.
Okay. Thank you very much.
Sure. How are you doing in the class?
I just a little bit confused about today's lecture.
Oh, okay.
Because there are so many graphs and yeah, I do not know like how to generate those numbers.
Okay. So maybe one thing that you want to do is to just refresh yourself about the definition of a graph and the definition of this BFS and DFS trees. Are you a computer science major or data science?
Applied data science.
Okay.
Yeah.
So these are common interview questions, right? People will ask you to write the code to trace a graph to generate a BFS trees or DFS trees.
Wait, what? Which question?
Generate trees from graphs.
This is for SDE position or for data science position or
any coding position. I think this is
Okay.
if you do leak code, this is probably on the easy level.
Oh my God.
And there are many different types of trees.
Oh, I did not take this.
Oh, Jin Chen said 570 talk about this. Yeah, that's algorithm. Algorithm will be is a very important class.
Okay. Thank you.
All right, sure. Anyone else? Bui, Wei Ren?
Hi, Professor. Oh, okay,
Go
you can go
ahead.
ahead. Bye.
Oh, Who wants to go first?
Okay,
Either
I go
way.
first. I have a question. Actually, from last week's quiz, when we're the first two questions, when we are calculating the prediction, whatever user-based or item-based, I'm not sure, is there a way for us to, well, when I was doing the quiz, I feel calculating these numbers, it really takes a lot of time, and that's why I cannot finish these two questions during quiz. So I want to ask if there is some technique or trick to remember when we are calculating this prediction.
There's no trick. The only trick is you have to do this many times, and that's why we want to do this in the quiz. I know that you probably do not have enough time to do this, to do the quiz for these two questions if you don't practice. But that's also why we dropped the two lowest quizzes.
Yeah.
Just to force you practice calculating all these numbers, because I think that's the only way. That's a good way to help you prepare yourself for any interviews.
Okay, so your idea is just more practice.
Yeah, there's no trick. It's like BFS, right? How would you write the code to do BFS? If you ask me to write it, I probably will not be able to do it. But if you want to write it very quickly during the interview, you have to practice. So it's the same.
Okay, yeah, because I feel, there are too many numbers, and when we are calculating the average, it's different when calculating the weight and when we're calculating the final prediction, and it's really easy to make errors when we're calculating.
Yeah, it is true. But
okay, yeah, just
there's
more
no
practice.
other ways.
Okay, thank you.
Sure. All right, Bui.
Hi, Professor. I have a question about the hash function in the main hash. In the homework, for the hash function, there's like the ax plus b mod m. Is there some requirement for the a, b, and n? Like, or is it arbitrary or random value?
Can you share the material? I'm not sure where are you talking about.
Just we need to define like 100 hash function
Yes.
in the homework, and is what are the coefficients? Is it random or any strategy?
Oh, yeah, that's random. I think you can just randomly pick ones.
There's no requirement. I
Yeah,
think
but that's a good question for your TA as well. I'm not sure how they encourage you to implement it, because I think in Spark or in some Python library, you can just pick hash functions. You can just generate hash functions.
okay. We just make sure that the mode value is greater than the number of hash function to make sure there is no confliction.
Yeah.
Okay. So, thank you.
Sure. All right, Weiren, Yijun, any questions? How's everybody doing in the class? Are you guys doing okay with the assignments and quizzes?
Wow.
I have to say it's not an easy course.
Of course, it's not an easy course. You pay
fast.
$8,000 for a course. I won't do an easy course for you. You have to learn something.
Well, I'm from computer science, but this course have much more workload compared to other computer science course.
Like which one?
No, I mean, generally speaking, this course has a huge workload compared to other
Oh,
not so easy computer science course.
by workload, you mean the homework assignments or readings? We don't have that lot of readings. Only homework assignment might take you more time.
Yeah, well, in total, I have to say everything.
I see. Yeah, but homework assignments are really good. I got many students after they graduate, they told me that the recommendation system homework and the project helped them a lot during the interview. So anything else? Thank you, everybody.
Yeah, I actually have a
Oh.
last minute question.
Sure.
Are you going to, do you have any research opportunities later, I mean, after this class?
Yeah, you can, if you do well in the class, you can contact me.
Okay.
And our PhD student can also interview you to see if there is a fit in the background.
I see. So like what time is a good time to contact you? Because I remember in the very first class you mentioned about this.
After the exam,
After the exam.
so that I know your performance.
Okay. All right, I think that's pretty much for today. Thank you very much.
All right. Thank you, everybody. Have a good night.
Bye.
I will see you next week. Work on your assignments.
Professor, I have some private concern about my homework too. I would
okay.
like to
I'll
go
just-
to a breakout room, or because you know
No,
this office hour.
we can just ask everybody to leave and I can talk to you.
But you know
Okay,
that
thank you,
this
Professor.
office hour will be recorded.
Thank you, guys. Yeah, I will stop recording.
Okay.